Number 6, review networking and reduce costs by deleting idle load balancers. Now, this one focuses on load balancers. I'm going to expand this a little bit. A load balancer just manages the load across a web fleet, for example, or you could have it balancing it a load across an application tier, like either like a front web facing tier or a mid tier application tier. You got a load balancer in front. For whatever reason, if you have idle load balancers, hunt those down and figure out if you can stop those. The other thing I would say from a networking standpoint is within your VPC, they have something in AWS called a virtual private cloud. And what that is, a logically separated, private, and secure environment that you carve out in the AWS cloud in which you provision your services in. Now, when you have compute or some other workload within your virtual private cloud or VPC that needs to get to, for example, simple storage service that I mentioned earlier, there are a number of ways to make this work. I'll give you three. You can attach an internet gateway, more commonly abbreviated as an IGW, to your virtual private cloud, and you can set a route for anything that needs to go out to S3 to take the next hop of that default gateway. And that'll certainly get you out to the internet to get over to your S3 from a public endpoint and a public API perspective. The second way you can do it is you can stand up a NAT gateway. A NAT gateway is abbreviated as a NGW. Now, the NAT gateway is analogous to an internet gateway in the sense that it'll get you out to the internet from your private subnets. However, what it'll do is it will mask your internal IPs. So that's nice from a security perspective. You're not seeing the IP addresses of your EC2 instances out floating around on the public internet. That's masked with a NAT gateway, and that'll get you out to the internet just fine to hit S3. Now, from a cost optimization standpoint, there's a problem with both of these. Even though they both technically work just fine, data out is a cost in AWS. Anything out is a cost. A NAT gateway is a resource that is a cost. Anytime you traverse a NAT gateway for the capability of keeping your private subnets, masking those private IPs, but doing the trade-off to say, yeah, we still need to get to the internet, both of those incur a cost. And guess what? I'm going to tell you how to neutralize both of those costs and still get you over to S3 without having to pay anything. And what you want to do is you want to attach what's called an S3 VPC endpoint to that virtual private cloud, the VPC. And then you'll set a route that any traffic that needs to go over to S3 to grab objects and buckets, traverse that S3 endpoint. And now you're riding the Amazon backbone over to S3 privately. You're not going out across that public S3 endpoint. And guess what? There's no charge for that because it's all considered private traffic. So it's not considered internet out. So that's just something that you might like. The other thing that I think would fall up under the concept of networking I talked about data transfer. So data transfer out incurs a cost. Data transfer back and forth between regions incurs a cost. Data transfer between availability occurs a cost. And I'm not going to get into the specific units or rates of those costs, but I would say just let's take it up a notch, high level. Let's say your compute workload is in Oregon and you set up in an Oregon region and you set up a S3 bucket. So you're storing data over in the AWS Ohio region. Now, when you go access data, you're going cross region from Ohio to AWS. And you need to really take that into account because that's not going to allow you to leverage that VPC endpoint because that VPC endpoint isn't mapped to the region, not all the way over to Ohio. So just something to think about there, your data transfer costs and how you're gluing your data flows together. If there's any way that you can influence things and co-locate them where it makes sense in terms of compliance requirements and security requirements to save on data transfer costs, make sure you do your due diligence there to index on that. Now, Amazon EC2 Spot to reduce your spend. What we've been talking about so far is the on-demand cost of compute resources and really an EC2 here. And on-demand relative to how you can pay the pricing constructs that you can leverage, relatively speaking, is on the high side in terms of how much it costs. There's other mechanisms that you can implement to lower your cost. And this is too is a hybrid in the sense that it's both a cost construct as well as an architectural decision you can make. So what is EC2 Spot? EC2 is the same compute that EC2 Spot is the same compute that you know and love in AWS. However, you can achieve a cost savings of up to 90% relative to the on-demand price, oranges to oranges and apples to apples, based on the EC2 instance family. Now, you might be saying to yourself, why wouldn't everybody just use EC2 Spot if it's 90% cheaper than just your regular EC2, if it's the same virtual server? The reason is that it's cheaper is that EC2 Spot is excess capacity in a given AWS region that associated availability zones in the region. So what that means is you can grab the excess compute in an AWS region and a set of availability zones at a deep discount. The trade-off is that if somebody comes into that same region and says, we want to spin up on demand the equivalent set of two instances within the same family, for the sake of this example, then that on demand, assuming that there's not enough excess capacity to both fulfill both your spot instance and that on demand instance would take precedence because that customer is willing to pay the on demand price as opposed to the cheaper price of the spot instance. So that means that your spot instance can be ephemeral in the sense that your EC2 compute instance can be reprovisioned back into the pool. So you lose your instance. Now you might be saying to yourself, why on earth would anybody want to use EC2 Spot? The answer to your question is quite a lot of customers want to use it. And when you're working with a solution architect like me, I can teach you how to what I call game the system. And game the system sounds scandalous, but you're not really gaming the system, leveraging capability that I would like you to leverage. If that makes sense. So the way you get around this is, and I talk this high level, when you have any application or service, you need to define the baseline level of compute. So this is the amount of compute that you need to run persistently. Now, there's some nuances here. If your workload is spiky and stuff, there's that. But let's say for the sake of this example, there's a baseline for how your application operates. Now, what you want to do for that baseline, you want to map either a reserve instance or a compute savings plan to that. Now, I've got ahead of myself a little bit here. I'm going to end this live today with a conversation on reserve instances and compute savings plans. But for the purposes of right now, I want you to realize that with EC2 Spot, you layer kind of your baseline compute with that reserve instance. So that's not going to be taken away. That's going to be persistent. And then if you want to auto scale, and which is basically fanning out your architecture wide like this, you can either bring on Spot is a good use case for this, or if you have a queue. So you have jobs that are being inserted into a queue. For example, on AWS, it's Simple Queue Service, SQS. You can have persistent workers that are reserve instances or on demand that's representative of your baseline. And then you can associate potentially an EC2 Spot fleet against that queue. Then a nice thing about a queue is that the other trick to this, which is not really a trick, it's an architectural decision you'll need to make, is that anytime an instance can potentially go away, in this case, EC2 Spot, you want to make sure that you're not storing any session state on those Spot instances. There's no session state on the Spot instances. That way, if they're pulled away, whatever compute is left, the remaining compute can just process it. So that's some architectural things you can do. So I think we've hit this pretty hard. One other thing I want to leave you with is that sometimes there's a perception that spot instances are very volatile. So, example, you'll spin up a spot instance and a minute later, boom, it's gone. It's not that volatile. In fact, the stats to the stability of spot instances in terms of how long they run before they're pulled away are very favorable for my customers. And you can search for that on the AWS website. Yeah, definitely want to take a look at Spot. Okay, I mentioned auto scaling groups, and I'm speaking a little bit out of turn here, but now we're catching up. So, an auto scaling group, for those that may not know, is typically associated with EC2. And you remember the example where I was telling you where you set up baseline level of compute? So, you'll have that kind of as your auto scaling group. And then let's say, for the sake of this example, that your application is bound by CPU. So, the more work that your application performs, the more sessions, the more transactions per second, or what have you. Let's say that that's proportional to the amount of compute that your application and your underlying servers would consume. You can set up an auto scaling group, which assumes that your application is able to scale horizontally. I'll touch on what it means to scale horizontally here in a second. But your application scales horizontally, and then you dynamically spin up additional EC2 instances. Those EC2 instances bootstrap themselves, and there's a level of architectural effort that you need to apply. It's not too difficult of a lift, but like I say, depends on your use case and how your application is designed. But your auto scaling group spins up more EC2 instances, and as those are added to the pool, the overall compute processing goes in aggregate. So that's what auto scaling groups do. Now we're looking at this through a cost optimization lens. So what does this mean? In an on-premises world, in a data center, you are just building out the application like for maximum capacity all year round. So you've paid big money for that. You don't want to do that in the cloud. You really want to map it to a baseline level of compute. And then those transient spikes that I mentioned, you want to map either on-demand instances to that and or spot. And that helps you to save money because you don't need to run, let's say, 10 servers simultaneously. Maybe you can cover the baseline of your workload with 4. And then as you need to scale up, you can add 1 or 2 servers at a time until that CPU utilization goes down, or and so on and so forth. Okay, I'm going to round out the remainder of this with conversation on reserve instances and compute savings plans, which is number 10. So this is a difference than everything we've talked about before. What we talked about before were architectural things you can do. Those architectural things that you can do are, there's a trade-off in doing those, in the sense that you got to dedicate some engineering resources to that. Now, with programmatic things like reserve instances and compute savings plans, you don't have to, it takes little to no architectural lift. Now, the way you do this is you look at your resources that you're using and you simply commit. It's time bound. Typically, the increments are 1 or 3 years, depending on what AWS services that you're hosting. And in exchange for that commitment, which is time bound, you can experience a discount for that respective level of compute. And the AWS site does a really nice job of explaining the various nuances to this. But what I would say is, before you blindly go in and just buy reserve instances or compute savings plans for that matter, you really want to ask yourself, is the stuff running is it optimized? And you can figure that out by following some of the architectural considerations that I mentioned in the first 8 things to take a look at. But yeah, so yeah, I recommend looking at reserve instances for RDS, which is the relational database service, Redshift, which is a massively parallel processing data warehouse, purpose-built in the cloud for AWS that runs at petabyte scale, or if you're using Redshift Spectrum, all the way up to exabytes. But that's outside of the scope of a deeper conversation on this call. Elasticache and Elasticsearch is where you want to really look at reserve instances. The other reason why reserve instances really fit nice here is that a Redshift cluster really isn't a transient workload. A lot of the customers I'm working with don't really spin up a Redshift cluster one day and tear it down the next. If you're doing data warehouse analytics queries, you're running huge queries, that's something that typically would be persistent and that would be running all the time. there's some caveats to that. You could potentially also augment your Redshift cluster with Redshift Spectrum so that you could separate your storage and compute needs. But that's another architectural thing you can do. But if you're using Redshift, you're happy with it and the way it's configured and it's your baseline configuration, you really do not want to pay on demand for that. If you're committed to that service, go ahead and attach an RI and yield those savings. And those can be pretty effective. After you're done purchasing the RI, it's pretty quick. The savings follow. Same thing with the RDS and Elasticache and Elasticsearch. So we're going to round out to the end here. Last one I was talking to you about here is compute savings plans. Now, I personally love compute savings plans, and I'm going to tell you why. Compute savings plans are a evolution of reserve instances. So reserve instances are great, but customers shared a lot of feedback with AWS, and they wanted some additional flexibility for a number of reasons. I'll give you one in particular. Let's say right now that you're running a predominant EC2 environment. If you were going to decide to stay in that kind of equilibrium for a year, then I would tell you, go ahead and attach yourself to a reserve instance and grab those savings. But if you were predominantly built on EC2, but you really wanted to make an effort in the near term to shift and modernize your application, you want to go through an application modernization effort. For example, you wanted to reduce your EC2 usage and do a shift over to, let's say, containers or Fargate or Lambda. Let me back up here a minute. Fargate is a serverless container orchestration service on AWS. Lambda is a serverless compute that runs your code or a function as a service within AWS. It's based on event-based computing. If you were going to do any of these, and I can tell you right now, a number of my customers that still happen to be on EC2, they're all headed to either containers and or serverless compute. This is where the market's going. I'm working with many startups. Both startups right now are doing it. I had enterprise customers when I was servicing enterprise customers formerly. The market is shifting to this. So if you're not doing that, you want to take a real close look to figure out how you can do this. But if you are, get a compute savings plan. The compute savings plan gives you real great flexibility. Not only will it reduce your spend on EC2, it reduces your spend on both Fargate and Lambda. Now, what it does is it takes those three services and it aggregates all the compute that each of those services consume, combines it together, and it gets what's called a compute per hour dollar amount. And when it does that, you can commit to a compute savings plan that is a map to that aggregate compute per hour amount, and then the bill drops. So you can map that to either 1 year or 3 years. And then there's some additional nuances there, kind of like whether you want to prepay that all up front, partial up front, no up front, and that would impact like the overall discount there for the compute savings plans. Now you may be asking yourself, how do I know what compute savings plan to buy? Go into AWS Cost Explorer, and there's going to be recommendations in there. Okay, so if you're not familiar with Cost Explorer, does a lot of cool things. It gives you great visibility. It allows you to run reporting into your AWS environments to see what things are costing. And it also recommends your compute savings plans where you should map this. You really want to go in there and look at that. But I was going to say, these are self-service things you can do. If you have any questions, go ahead and place those down in the comments, and I'll come back and address them. I'll see you next time. Take care, everybody.